Okay, so today we're going to be trying to find the component form of vectors given initial points and final points. So this problem states find the component form and length of the vector with initial point p equals -3, 4, 1, and terminal point q equals -5, 2, 2. This might be one of your first interactions with vectors, so I'll quickly draw a small picture just so that you can visualize it a little bit before we jump into this problem. Make this the z-axis, x, and y. So our point P, which I'm going to do in red, is -3 on the x-axis, so we're going to go out to here. And then it's going to be +4 on the y-axis. We'll go about here. And just one unit in the z-axis. We'll go here. So this is what we'll call our point P. And Q, we'll see it's -5 on the x-axis, so a little further than P. And it's going to be only 2 in the ways of the y-axis, so here. And it's going to be +2 in the z-axis, so a little higher than P. And so our vector with them combined would be this here. The purple is the vector PQ, from P to Q. So what's asking is the component form of this vector. And if you have any sort of physics background, you might remember that the net velocity, for example, is the final minus initial. It's the same concept here, where in order to find the net displacement, you could say, we're going to be taking our final points, the final values, which are our Q values, and from those we're going to be subtracting our initial value. And our initial values are the p values. So the vector PQ in component form is the final value minus initial value. And I'm getting these x values from Q and P. So those are the x values, and then the final y value minus the initial y value, and the final z value minus the initial z value. And if we work this out, we get -5 minus -3, which is -2. 2 minus 4, -2. And 2 minus 1, 1. So this is our component form. This is our x, our y, and our z values. So now to find the length, I'm going to use an example, a 2D example at first to explain it if you're encountering this for the first time. Remember back to the Pythagorean theorem. So in the Pythagorean theorem, you'd probably remember seeing something like this, where you have a right triangle of sides A, B, and hypotenuse C. And you have the formula a squared plus b squared equals c squared. Now, if you want to find just c, just the length of c itself, you're going to want to solve for c in this equation. So this equation becomes c equals the square root of a squared plus b squared. So you take the two sides, you square them, and then you take the square root of their addition. It works the same way with vectors in 3 dimensions. So in this case, we're going to be taking our x component, our y component, and our z component, and we're going to be squaring them, adding them, and then taking the square root. It's the same idea as the Pythagorean theorem, just in 3D. So let me do that for you now. We use the form, it almost looks like absolute value bars to show length or magnitude, and sometimes you'll see 2 absolute value bars. Both are valid ways to show the length. So we're going to take the square root of our final components for PQ, so -2 squared plus -2 squared plus 1 squared. All right, and again, these are just carrying straight down. And that's going to equal the square root of 4 plus 1, which equals the square root of 9, which is 3. So the length of the vector PQ is 3.